All right, welcome back. Glad to have you with us for another deep dive. This time, we're taking a look at something you requested. Efficient polynomial multiplication using the Fast Fourier Transform, or FFT for short.
That's right.
And, it might sound a bit, well, abstract or maybe even a little intimidating at first glance.
Sure.
But trust me, there's some truly elegant and powerful math hiding beneath the surface here.
Absolutely.
So we're going to break it down, really get a feel for how the FFT takes what could be a very, very slow process, especially when you're dealing with these really long, complicated polynomials, and turns it into something much, much faster.
Yeah, I think a lot of folks probably remember back in algebra, multiplying polynomials like, say, a plus bx times c plus dx.
Right.
You'd multiply each term in the first one by each term in the second one. You get ac plus adx plus bcx plus bdx squared. And, for simple cases like that, it's pretty straightforward.
No problem.
But imagine polynomials with hundreds or even thousands of terms. That method quickly becomes a computational nightmare.
Oh, absolutely. It's that dreaded theta n2 complexity, right?
That's right.
Where n is, roughly the number of terms in these polynomials.
Yeah.
As n gets large, that squared term really starts to dominate. So today we're going to figure out how the FFT algorithm provides this incredible shortcut, bringing that complexity way down to a much more manageable theta n2.
All right.
And a big part of the magic here, a real shift in perspective, is how we think about representing these polynomials. We're going to go beyond just manipulating those coefficients and step into a whole different way of looking at them.
Right. It's all about understanding this interplay between the coefficient representation, the one most people are probably familiar with, just those numbers in front of the powers of x, and then this point value representation.
Oh, point value representation.
Yep.
That sounds intriguing. But first things first, let's make sure we're all on the same page. How do we describe a polynomial in the first place?
Right. So the summary talks about these two key representations.
Exactly. Two key representations.
And, the first one, the coefficient representation, it's the most natural one to start with.
Yeah, I think that's the one we all kind of learn first.
Exactly. So if you have a polynomial, let's call it edox, and it looks something like, $t plus a1x plus an1 x1, then the coefficient representation is just that ordered list of the coefficients. A dollars, a1, a1.
Okay, nice and straightforward.
Exactly. And, if you want to add two polynomials in this form, it's super easy. You just add the corresponding coefficients.
Right, line them up and add.
Exactly. And that only takes theta time because you're just doing n additions. Even if you want to figure out what the value of the polynomial is at a specific x using something like Horner's rule, that's also pretty quick. It's also theta.
So coefficient form, great for addition, great for evaluating. What's the catch?
Well, the catch is multiplication.
Ah, there it is, multiplication.
That's where things start to get a bit messy. As you mentioned before, with that theta n2 complexity, when you multiply two polynomials in coefficient form, each term in that first polynomial needs to be multiplied by every single term in the second.
Yeah, it gets kind of combinatorial.
Exactly. So you end up doing roughly $1 times not individual multiplications, and that's where that theta n2 time complexity comes from. And as the summary highlights, this multiplication in coefficient form actually has a very close connection to another mathematical operation called the convolution of the two coefficient vectors. It's like they're fundamentally linked.
Okay, so multiplication in coefficient form, not ideal. That's where our second representation comes in, right? The point value representation.
Exactly. That's where things get really interesting.
All right, lay it on me. What is this point value representation all about?
So instead of listing out the coefficients, we describe the polynomial by a set of, let's say, not distinct points that it passes through. So for a polynomial x with a degree bound of land, we'd have nollier pairs of x and y values. $7, y1, 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 x, y1.
Okay, so we're talking coordinates on a graph, essentially.
And each while is just the value you get when you plug the corresponding cas into the polynomial. And here's the key. If you know those nollier different x values, and the corresponding y values from a polynomial with a degree bound of nollier, that polynomial is totally unique. There's only one polynomial that can fit all those points perfectly.
It's like those points create a fingerprint that uniquely identifies that polynomial. I like that.
That's a great way to think about it. And that idea is actually formally proven in theorem 30.1, which the summary mentions. It states that a polynomial with a given degree bound is completely determined by that many distinct point value pairs.
Okay, so point value representation, unique fingerprint, got it. But how does this help us with our multiplication problem?
Well, the really cool thing about the point value representation is how it changes the game for addition and multiplication. Let's say you have two polynomials in bovet x, both with a degree bound of $, and you have their point value representations at the same distinct 6 of points.
Okay, so we've evaluated both polynomials at the same set of x's.
Exactly. To add them together, you simply add the corresponding y values at each sixillar. So you just go point by point adding the y's.
That sounds pretty easy.
It is, and it takes just theta time because you're just doing additions.
All right, so addition in point value form is a breeze. What about multiplication?
Multiplication's also very efficient in this form, but there's a slight detail we need to keep in mind. When you multiply two polynomials, each with a degree bound of $, the resulting polynomial will actually have a degree bound of $2.
Right, because those highest power terms multiply together.
Exactly. So to uniquely represent this product in point value form, we need 200 point value pairs. However, if we do have 200 pairs for each polynomial, all evaluated at the same 200 points, then multiplication becomes incredibly simple.
How so?
We just multiply the values together point by point. Again, that takes only Tada's time.
Wow, so addition and multiplication become super efficient in this point value world. That sounds almost too good to be true. What's the trade-off?
The trade-off is the conversion process. Going back and forth between the coefficient representation and this point value representation can be computationally expensive if we're not careful.
I was wondering about that. We can't just magically jump between these two forms without some work, right?
Right. If we want to go from coefficients to point value form, we essentially need to evaluate the polynomial at different $6 values. If we do that naively, using Horner's rule or something similar for each evaluation, it'll take theta n2 time overall.
Back to square one.
And going the other way, from point value back to coefficients, that process is called interpolation. The straightforward methods for doing that, like solving a system of equations or using Lagrange interpolation, can also take theta n2 time, or even worse, sometimes theta n3 day.
Ouch. Now, we've traded slow multiplication for potentially even slower conversions. Not exactly a win. That's where the Fast Fourier Transform comes in now.
You got it. The FFT is like the bridge that makes this whole strategy actually work.
Okay, so walk us through that. How does it make those conversions fast?
The summary outlines a really clever four-step process. First, take your two polynomials, both in coefficient form.
All right,
Second, we might need to pad them with some extra zero coefficients to make sure their degree bound is a power of 2, like 2 in Mellon.
Okay, so a little pre-processing step, making sure they're the right size.
Yeah, exactly. Right. Now, here's the really crucial part. The third step. We evaluate both of those polynomials, which might now be a bit longer after the padding, at a very specific set of 2 nuller points.
Okay, and those points are?
The complex roots of unity.
Ah, the complex roots of unity. Now we're getting to the heart of the matter.
That's right.
But before we get too deep into those, maybe let's take a step back. What exactly are complex roots of unity for those who haven't encountered them before?
So a complex root of unity is a complex number, usually denoted as omega dollar, that has the special property that when you raise it to the power of nuller, you get 1. In other words, omegan equals 1.
Okay, so it's like a special kind of complex number that cycles back to 1 when you raise it to a certain power.
Exactly. And it turns out there are exactly distinct complex numbers that satisfy this property for any given dollars. They're evenly spaced around the unit circle in the complex plane, and you can represent them using Euler's formula as EP ektha, where it ranges from 0 to day 1.
Okay, so they're like these evenly spaced points on a circle, and they have this special cycling property. But why are they the key to making our polynomial conversions fast?
Because they have some amazing properties that the FFT exploits to its advantage. The summary mentions 3 key lemmas or helpful mathematical truths that really illustrate this.
All right, let's hear those lemmas.
The first is the cancellation lemma. It states that omega decant.
Okay, lots of omegas and exponents there. What does that actually mean in simpler terms?
Well, it essentially says that if you have a root of unity of a larger order, like d dollars, and you raise it to a power that's a multiple of dollars, you can simplify it down to a root of unity of a smaller order, not raised to the corresponding smaller power.
So it's like we can reduce the complexity by canceling out those extra factors of a dollars in the exponent.
Precisely. And a really useful consequence of this lemma is that omega t and a t stand on 1. This seemingly simple fact turns out to be incredibly handy when we delve into the FFT's divide and conquer strategy.
Okay, to make it end on, I'll keep that in mind. What's the next lemma?
The next one is the halving lemma. It says that if naught is even, then the squares of the non-complex roots of unity are exactly the two Don-Toxoplex and two Thoth roots of unity. And what's even more interesting is that each of those n-Thoth roots appears twice when you square the original Dorn roots.
So squaring those non-complex numbers doesn't give you dollar distinct results, but only $2 too.
Exactly. And this halving property is crucial for the FFT's efficiency because it allows us to break down a problem of size $1 into two smaller, self-similar problems of size $2, That's the essence of divide and conquer.
It's like those roots of unity naturally want to be divided in half.
Exactly. Now, the third important lemma is the summation lemma. It states that for any integer $1 and any non-zero integer dollar that's not divisible by 9, if you sum up all the powers of $1 from $1 to $1, the result will always be 0.
Okay, that one sounds a bit more abstract.
It is a bit more abstract, but it plays a crucial role in proving the correctness of the inverse DFT, which is the process of going from the point value representation back to the coefficient form. It ensures that we can reverse the transformation and recover our original polynomial.
All right, so we've got these complex roots of unity with their cancellation, halving, and summation properties. How do they help us connect our polynomial coefficients to that point value representation? That's where the discrete Fourier transform, or DFT, comes in, right?
You got it. The DFT is the mathematical operation that bridges the gap between those two representations. So the DFT of a coefficient vector A1, AN1, is a new vector yn1. Each element in that new vector is calculated by taking our original polynomial xx and evaluating it at the tact root of unity, which is omega.
So we're plugging those special roots of unity into our polynomial.
Precisely. Mathematically, that looks like this. Omega n1 a aj. So the DFT takes us from the world of coefficients to the world of point value pairs, where each color represents the value of the polynomial at the corresponding root of unity. And we often use the notation general text DFT well to represent this operation.
Okay, DFT equals coefficients to point value. Makes sense. But we still haven't tackled the speed issue. If calculating this DFT still takes that into time, we haven't gained anything.
Right. And that's where the Fast Fourier Transform, the FFT, comes in. It's a super efficient algorithm that computes the DFT in theta LD time. But it works best when n is a power of 2. If it's not, we can just pad our polynomial with some zeros to make it the right size.
All right, FFT is speed boost. But how does it achieve that speed boost?
Through that divide and conquer magic we talked about. Let's go back to our polynomial LDX HLDX plus A1x plus A2 by 2 plus LG plus A1 Elabura. The key is to separate the terms with even index coefficients from those with odd index coefficients.
So split it in half based on the powers of 6.
Exactly. We can rewrite EH2 plus x by 2, where ATX contains all the even index coefficients and ATX contains all the odd index coefficients. And notice that both of these new polynomials have a degree bound of 2 LG2, half the size of our original polynomial.
Okay, so we've broken it down into two smaller pieces based on the evenness or oddness of the exponents.
Right. Now, when we want to evaluate our original polynomial at the knoth roots of unity, say at omegainc, we can use this new form, 1 plus omegainc 2 plus omegainc 2. But remember the halving lemma. It told us that squaring a nth root of unity gives us an nth root of unity.
Ah, so those squares simplify things.
Exactly. So evaluating at nthity at len2 is like evaluating polynomials of half the size at the n2 roots of unity.
So we've reduced the problem to two smaller, self-similar DFT calculations.
Precisely. And the FFT algorithm exploits this recursive structure. It keeps breaking down the problem into smaller and smaller DFT computations until it reaches a base case where the polynomial is trivial to evaluate. Then it combines the results from those smaller DFTs using those twiddle factors, which are powers of McGangan, to get the DFT of the original polynomial.
Wow, so it's a beautiful divide and conquer strategy that takes advantage of the special properties of the roots of unity to achieve that theta time complexity.
Exactly.
Okay, we've efficiently gone from coefficients to point value using the FFT. Now we're in the point value world where we can do our super fast multiplication, but how do we get back to the coefficient world to see our final result?
That's where the inverse DFT comes in. It takes us from those point value pairs back to the coefficients of the product polynomial. And as the summary mentions, the DFT can be represented as a matrix multiplication. Y is a PFT and AI, where $5 is a special matrix called a Vandermonde matrix. The inverse DFT is just the inverse of that operation, A of TM-1Y VM1YY.
So we're essentially undoing that matrix multiplication.
Right. And the really cool thing is that the inverse of this Vandermonde matrix has a very specific specific form. Its entries are tomegan J and OA.
Wait a minute, that looks almost exactly like the formula for the forward DFT, just with a negative exponent and divided by nuller.
That's right. It turns out the inverse DFT can also be computed in theta, LGN time, using an algorithm that's very similar to the FFT. You essentially run the FFT again, but with a few tweaks. You swap the input and output, use the conjugates of the roots of unity, and divide by nuller at the end.
So the FFT algorithm can be used for both the forward and inverse transforms. That's so elegant.
It is, and it's one of the things that makes the FFT so powerful and efficient.
All right, let's recap the entire process for fast polynomial multiplication using the FFT. We start with our two polynomials in coefficient form. We pad them with zeros if necessary, and then use the FFT to convert them to point value form by evaluating them at the complex roots of unity. That conversion takes theta time for each polynomial.
Right.
Then in point value form, we multiply the values together point by point. That's super fast, only theta time. Finally, we use the inverse FFT to convert the result back to coefficient form, which gives us our final answer. And that inverse FFT also takes theta on LGN. So the overall time complexity is dominated by those three FFT steps, giving us theta, which is a huge improvement over the traditional theta-del method for large polynomials.
Absolutely. And the summary also highlights a really fundamental connection between polynomial multiplication and the DFT through something called the convolution theorem.
Oh, right, the convolution theorem. It's not just a random trick. It's deeply tied to the math of convolution. Tell us more about that.
Well, the convolution theorem essentially states that the convolution of two vectors, which, as we discussed, is closely related to polynomial multiplication, can be computed by taking the DFT of both vectors, multiplying those DFTs pointwise, and then taking the inverse DFT of the result. So since polynomial multiplication corresponds directly to convolution, the FFT provides a super efficient way to perform that convolution and therefore polynomial multiplication.
I love how it all ties together.
But yeah, it's really elegant.
Now, the summary also briefly touches on how this whole process can be implemented directly in hardware using specialized circuits.
That's right. For applications where speed is critical, like real-time signal processing, having dedicated hardware for the FFT can be a huge advantage.
How do those FFT circuits actually work?
They exploit that divide and conquer structure of the FFT algorithm. The basic building block is something called a butterfly operation. It combines two input values using a specific twiddle factor, which is just a power of omega, to produce two output values.
Butterfly operation.
Yeah.
Sounds kind of poetic for a mathematical operation.
Oh, right. And a non-input FFT circuit typically consists of Delaller stages, each with 200 the tollers of these butterfly operations that can all happen in parallel. So you can imagine the speed benefits.
Yeah, parallel processing can really make a difference.
Excellent.
Now, one last thing I wanted to mention. The summary concludes with a really helpful glossary of terms, which I think is fantastic for anyone who wants to really dig into this topic further. It covers everything from basic concepts like polynomial and coefficient representation to more advanced terms like complex derivative unity, DFT, FFT, convolution theorem, and of course our friend the butterfly operation.
I think that glossary is really valuable. It's a great reference for those who want to explore this topic in more depth.
All right, so to wrap it all up, we've seen how the Fast Fourier Transform provides a blazingly fast way to multiply polynomials. It does this by leveraging the special properties of complex roots of unity to efficiently switch between the coefficient and point value representations.
Yeah.
This allows us to exploit the speed of pointwise multiplication in the point value domain and ultimately achieve that impressive theta-endl time complexity.
Yeah, it's a brilliant combination of mathematical insight and algorithmic cleverness.
And I think what's really fascinating is how this fundamental idea of transforming a problem into a different domain where the operations become simpler has applications far beyond just polynomial multiplication. It makes you wonder, what other problems could we solve more efficiently if we thought about them in a different way, in a different space? It's a really powerful concept.
Absolutely. That idea of transforming a problem to simplify it is at the heart of so much of mathematics and computer science. It's a great takeaway from our depth dive today.
Well, this has been a truly illuminating exploration of the Fast Fourier Transform and its role in efficient polynomial multiplication. Thanks for joining us on this deep dive. We'll see you next time.